Hey everyone, and welcome to today's Physics Daily Booster. This is number 6 in our Paper 2 series, and while it's not explicitly listed on the advanced information for either the Physics Higher or Foundation, it's highly unlikely that there will be no questions on Unit 6. So I would say highly relevant still, because there's going to be some questions on it. What we're going to start off with then is a bit of a recap on something that hopefully we know from our first chemistry paper, and that is the structure of an atom. Hopefully we do remember that in terms of the atom, then we have this nucleus, which is made of protons and neutrons, and then the electrons are in shells around it. There's that very familiar table in the middle there, which is showing us our 3 subatomic particles, protons, neutrons, and electrons, their relative masses and relative charges. So once more, you just need to learn these. So proton relative mass is 1, relative charge plus 1. Neutron, relative mass 1, relative charge 0, neutron. Electron is the relative mass of 0.0005 or 1 over 2000, and its relative charge minus 1. Now, do remember that if we're talking about our nucleus, that's made of just the protons and the neutrons. So protons have a positive charge, neutrons have no charge. So what we actually find is that means the nucleus is always going to be positive. We do have a familiar definition here as well. Isotope, an atom with the same atomic number but a different mass number, or it has the same number of protons and electrons but a different number of neutrons. So make sure you know the definition for isotope. Given us 3 different examples here of isotopes of carbon, carbon 12, carbon 13, carbon 14. So what we can notice is the atomic number is always 6, so that means we always have 6 protons and 6 electrons. The mass number, however, we've got 12, 13 and 14. And if you remember, in order to work out how many neutrons there are, what we do is our mass number minus the atomic number. So in this case, 12 minus 6 is 6, 13 minus 6 is 7, 14 minus 6 is 8. So we can see that the number of neutrons is different in each of those isotopes. One thing that we should remember is that usually most atoms are stable, and by that we mean that they do not decay. Some atoms, however, are what we refer to as unstable. So that just means that they are going to undergo this process of decay, and as they do so, they emit radiation. Now, any material that emits radiation is termed radioactive. We have 4 types of radiation we need to know about: alpha, beta, gamma, and neutron. First of all, alpha radiation. This is a particle, the alpha particle, which we're going to describe as the nucleus of a helium atom. So in terms of what we would use in an equation with alpha decay occurring, it is going to be our little sign for helium, He, 4 and 2. So remember the equation symbol for the alpha particle. Beta particles, these are fast moving electrons, and there is their little equation symbol. Gamma is not a particle, it's an electromagnetic wave. So because of that, it doesn't have an equation symbol because it is just energy. Then we've got neutron, which is a particle, and you can see the symbol we would use in equation at the bottom there, little n for neutron, and then obviously the mass and the atomic number. It is worth remembering that neutrons can actually undergo decay themselves in order to make a proton and an electron. One of the old favourites on the radioactivity part is looking at the experiment that hopefully you had demonstrated to you, which uses this thing called a Geiger tube or a Geiger counter to actually record the amount of radiation being emitted by different sources. So you'd have seen little numbers counting up on a screen, and if they'd actually connected the sound up, you'd have heard these little clicks as you go. Now the little clicks, you can hear tiny currents produced when the radiation ionizes atoms of gas inside the Geiger tube. This little diagram at the bottom is probably the easiest way to remember these key facts about the alpha, beta and the gamma. Alpha radiation then is going to be stopped by a few sheets of paper. Beta radiation goes straight through the paper but is stopped by a few millimeters of aluminium, and gamma radiation straight through the paper, straight through the few mils of aluminium, and is only going to be mostly stopped by a few centimeters of lead or meters of concrete. So what we can work out here is, as we go alpha, beta, gamma, so as we work our way down, the penetrating power is going to increase, i.e. they're going to travel through more things. They can also phrase this in the way of giving you readings from a Geiger tube when we've passed it through different materials, i.e. paper, aluminium and lead. And then they will ask you to identify the actual types of radiation present. So what we find there is, if you've got one that's got obviously a high activity beforehand, and then the activity drops right down after it's been passed through paper, we can say alpha is there. So all we're doing is really applying what we know here as these key facts about what's going to stop those types of radiation to work out what's present. Now, what we also need to consider is the ionizing ability, so the ionizing power of these different types of radiation. We've looked at the penetrating power, now the ionizing power. If we have a look at our little summary table here then, what we can see, we've got alpha, beta, gamma. You can see the relative masses linked into those equation symbols we saw earlier. Charges, again, back to the equation symbols. And then we've got the ionizing power. So you can see alpha is actually the highest. And all we do is work our way down. So alpha has a high ionizing power, but a short range. Beta is dead in the middle for both. And then gamma has a low ionizing power, but it has a long range. When we're talking about ionizing, this is basically the ability of that radiation to remove electrons from atoms and therefore form ions. So in order to ionize an atom, we've got to transfer energy to it. What we find, the reason that the alpha particles have the highest ionizing power is just that they're going to transfer more energy to the material, and as a result of that, they only have a short range because the energy is going into ionizing something, and therefore it's not going to travel as far. You do need to know about the decay equations, and in several years they actually give you 2 marks for each of them, and sometimes they give you 3 of these decay equations. So could be a nice easy 6 out of those 90 marks if they do it again this year. What we're looking at then, in alpha decay first of all, we are going to emit an alpha particle. As we said earlier, that helium nucleus, the alpha particle, is made of 2 protons and 2 neutrons. So what we will see is, if we look at the little equation here, we start off with an element which has got a mass of 240 and an atomic number of 94. We are then going to form something and an alpha particle. So if we remember, our alpha particle is the helium, 4 and 2, 4 is the mass, 2 is the atomic number. So in order to work out what this bit is, quite simply, all we need to do to get the mass is 240 minus 4, that gives us 236. And then to get our atomic number, all we need to do is 94 minus 2, which gives us 92. They give you these with various bits missing, okay? So all you need to do is remember that whatever the numbers on the left are, the ones on the right are going to add up to the same totals. And if you know the helium numbers, then you've got no problems doing that. Beta decay then. What we find in beta decay is a neutron is going to decay into a proton and an electron. So here's our equation again. We're starting with carbon with a mass number of 14, atomic number of 6. Remember what we're saying happening. A neutron is going to decay to form a proton and an electron. So because of that, the mass number is not going to change, because while we lose one neutron, we're then gaining the proton. So the mass number stays the same, stays at 14. And remember, in terms of our beta, there's our symbol, the electron, 0, minus 1. Now we are forming a proton, and remember your atomic number is the number of protons. So we start with 6. If we're forming a proton, it goes up to 7. Third one, gamma. If you remember what we said earlier, gamma rays have no mass or charge because they are just electromagnetic waves, they are energy. So that means there's no change to the mass or the atomic number. What you start with is what you end with. And finally, neutron decay then. Here's our little equation at the bottom. What we find is that the decay of some of these nuclei leads to a production of large numbers of neutrons. And then we've got to emit those neutrons in order to make it stable. So here's our example. We've got helium, which has got a mass number of 5, atomic number is 2, and if you remember, there is our symbol for our neutron. So mass is 1, atomic number is 0. What we then do is, by those same rules we had earlier, remember the mass number on the left must equal the mass numbers on the right. So if we've got 5 on the left, and we know the neutron has a mass of 1, the other thing must be 4. And then we've got atomic number of 2 on the left, neutron nothing there, and therefore it must be 2 for our other one. So this is quite simply just a case of adding or subtracting from what they give us, and knowing obviously the element symbols for the types of decay. If there are any bits that we've gone through today that you'd like to look at in more detail, then you can use the P6 playlist over on the channel. Obviously use your revision guides and do have a look at some of those past exam questions to get a bit of a feel for it. We will not be back with a daily booster tomorrow because in fact we are going to be doing the live stream for paper 1. So that will start at 6 PM on the channel. We'll go through everything for P1, P2, P3 and P4 for those of you doing triple science. And then for those of you doing combined bit, we'll cover everything on P1, P2 and P3. Foundation and higher, everyone welcome. Daily boosters will then be back on Friday the 10th of June for our physics.